This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Welcome to Lecture 23, everyone. And today we're going to look a bit more at the actual underlying hardware of FETs and how they go into making up logic gates, etc. So last lecture I showed you a simulation of the input-output relationship of an inverter, and it's important you understand what that graph is telling you. So that was for the steady state behaviour. Along the horizontal axis was the input voltage to the inverter. So in other words, we were interested in the behaviour of an inverter, which you normally see like this. We had worked out that that circuit symbol actually gets implemented in hardware using two FETs that look something like this. So that's the inputs here and the outputs here. And the first graph I showed you in the simulations, I had the input voltage down here and the output voltage up here, and I was looking at the steady state response. That's another important thing. It means that to plot this graph down here, I first of all pick an input voltage, I apply that input voltage, and I wait. In principle, I wait a very long time until the output is no longer changing. In practice, you don't have to wait very long at all. And then you plot that point. Then you increase the input voltage a bit, and you wait and wait until the output has stopped changing. And then you plot the output voltage. And this gives you the input-output transfer function, or the input-output response, whatever you want to call it. And you should all remember what this looks like for an inverter. A real inverter looks something like that. Any questions? Very good. That's from last lecture. And in fact, we already did this last week, so this is revision. The ideal, so that was the actual input-output response of an inverter. The ideal input-output response is this. That's the ideal one. So a real one looks a bit more like, well, I'm not very good at drawing, but the real one looks a bit more like that dotted thing that you can't really see. And the ideal one is flat along the top, drops down immediately, and is flat along the bottom. And then I asked the question last lecture, why is this ideal? And I'll be reminding you of that on the next slide. Any questions so far? I'm just revising what we did last lecture, but you might have thought of a question between now and then. No, it's all under control. So why is this? Why should an inverter have a transfer function that looks like this? So in fact, maybe to put this question in perspective, if I lived in the perfect world where for digital systems 0 was 0 volts, 1 was 5 volts, and there was no noise and whatever, all that would really matter is that if I applied 0 volts into my inverter, I get 5 volts out, 0 in gives me a 1 out. And if I applied a 0 to the, so if I applied a 1 to the input, which means 5 volts, I get a 0 on the output, which gives me an output like that. In an ideal world, all I need is my inverter to behave like this, and whatever happens in the middle, who cares? You can do anything in there. Because in an ideal world, you'll never be anywhere in the middle. The input will be perfectly 0 volts or perfectly 5 volts, and the output will therefore be perfectly 0 volts or perfectly 5 volts, and we don't have to worry. But yet in the real world, we want a transfer function to look as close as possible to this. And there are two reasons. The first is we want to minimize delays. So what do I mean by that? Well, here's my inverter appearing at a random place on the page, and if I and now I'm plotting something different. Now I'm plotting an input waveform with respect to time. If my input waveform is originally 1 and then drops down to 0, then ideally I want the output of my inverter to rise immediately up to a 1. That's ideally what I want, to have no delay. Now, delays are actually to do with the transient response. So the delays are largely determined by things that this input-output relationship doesn't show us. Okay, there's capacitance in there or whatever. But putting that aside, if my transfer function looked like, let me get this round the right way. So I was going from a 1 to a 0. So if my transfer function looks something like this, then you see we have to wait for the input to drop a long way before the output suddenly changes. So this thing to minimise delays is essentially saying that we want the transition to be halfway between the two extremes. It's not the best actually. I might take it out of next year's slides, but it's better than nothing. So that's one reason. The more important reason is we want to maximise robustness to noise. And I mentioned this last lecture. I'll repeat it here. Then I'll show you in an actual simulation what happens. The input is rarely going to be very clean. The input will have some noise on it. Even if I have a piece of wire here, it'll have noise on it. There's probably going to be 50 hertz picked up from the power lines. There's going to be thermal noise in there. You're always going to have noise. So the input signal might be wiggling around a bit. And if the input signal is wiggling around a bit here, then the output can change a lot. A small change in the input can produce a large change in the output if it followed that transfer function. So the main advantage, the main reason for wanting this guy to look like this is that the input voltage can change a lot and the output voltage doesn't change at all. That's what gives you robustness to noise. And I will show you that in SPICE simulations to make it triply clear. Any questions at this stage, though? Okay. Sorry, I just want to make sure it hasn't skipped anything. Yeah, okay. So you remember in your mid-semester test, one of the multiple choice questions was along the lines of digital systems are robust to noise. That's what we mentioned early on in this course. One of the advantages over analog systems is that digital systems are robust to noise. That means precisely that the input might be noisy, it might fluctuate a bit, but the output should be very clean. The input being noisy means it's not exactly 0 volts and not exactly 5 volts, and it might be oscillating up and down a bit. That's what we mean by noisy. And the amount of noise is given by the amount of fluctuations there. How much larger can the input go above 0 volts? How much lower can it go below 5 volts? That's sort of the amount of noise there. Where does this noise come from? Well, it could come from previous gates not doing their job. Could come from crosstalk. Remember we mentioned that digital design, once you hit the PCB, becomes analog design. As soon as you run traces on your PCB, they are transferring information using electromagnetic waves. It's actually got very little to do with the electrons zooming along the copper traces. It's actually the waves in between the traces that carry all the signal, etc. And you get crosstalk, meaning you send a signal down this pair of wires, this other pair of wires is going to get interference from it, and you'll get these oscillations there. When you've got digital circuitry switching very quickly, you get huge spikes in the power rails, And these power rails are connected to all sorts of other chips there, and so you get noise everywhere. Digital circuits are actually very noisy circuits. And so it's important that they can clean up the noise. Later in the lecture, I'll give you an even more precise definition of what we mean by noisy and cleaning up, etc. But that's good enough for now. So I tried to show you before with diagrams why logic gates reduce noise, and I'm now going to show you with a SPICE simulation. And in fact, if I don't mess it up, I'll actually try to show you how you can do it using SPICE yourself to see if I can get you interested in playing around with SPICE. Now you like playing around with Quartus and Model Sim, you might find you like LT SPICE. So what you can do at home is grab the two inverters in series, hit the copy, and then do there might be a fast way with Windows. I normally use Linux, not this Windows rubbish, but anyway. Hit the paste, I'll leave it at that name. So this is a copy of the two inverters that I showed you last week. Remember that this is one inverter and this is another inverter. This is just the supply voltage here, happens to be 3.3 volts, and this is the input, which is currently a pulse here. So this gives me a nice clean pulse, 0 volts, 3.3 volts. I want to add some noise. Rather than add random noise, I'm going to add a sinusoid to the input. That's good enough for noise. So now this might be a bit embarrassing. Let's see how much I remember of SPICE. So if you go up here, it's got move and drag. Drag should keep the connections for me. So if I select this, I can drag it over here. I now want to add another voltage source to give me a sinusoid in here. So if I go somewhere to edit component, so this is the slow way of using it. If you become an expert, you can zoom along with keyboard shortcuts and everything. I select a voltage source to put in here, and this turns to look like a voltage source, and I just stick it right here. Now press escape to get rid of that. I don't want this ground here, I want the ground down here. So again, in the interests of cheating, I do drag, try to select this ground, move. Wrong one. This is when you want move, in fact. Move, grab it, move it down here. Now R's rotate, so Control R should rotate this doohickey around. And then I just stick it on there, so I now have a ground here. If you're a perfectionist, you don't like wires sticking out into nowhere, so you can grab the scissors and just snip that off there. And the last thing I need to do is tell it what sort of a voltage source this is. So I right-click on this. Hello. Right-click on it again. Click Advanced. Select a sinusoid. DC offset, so I just wanted it 0, that's good enough for me. The amplitude, well, we can vary this, but let's start off with 0.5 volts. The frequency, now this pulse over here, it's around a gigahertz or something, so I'll make my frequency 5G, 5 gigahertz, and that's good enough. I can leave the others blank. And so now if I haven't made too big a mistake, I've got my original square wave pulse going in there, a digital signal, and now I've added a sinusoid there to represent some sort of noise going in. Hit the little man up here for run, get out my probe, and let's have a look at the input that I've generated. And don't know how well you see the green there, but it's not a crown, but it is my square wave input with a fair bit of noise here, right? That's a very noisy signal, not a perfect 0, 1. And let me have a look at the output of sending it through two inverters. And look at that. Very, very clean, a very, very clean signal. Of course, there are these delays and there are these funny transitions. I did say digital circuitry is very noisy. But after that delay, and remember I did say so many times in the lecture that we've got contamination delay and propagation delay, and in between the two we have no idea what the signal is actually doing. Well, in between the two, that's when you get all this mess. But who cares what's happening in there? We look outside of that and we've got a very beautiful 1 here and a very beautiful 0 there. So that's what we mean when we say digital circuits tidy up the signal. Noise comes in everywhere, but as soon as it goes through another logic gate, it's removed almost all of the noise. And it's because the input-output relationship is very flat, very steep gradient, very flat again. You can play around at home with different amplitudes, etc. Of course, if the noise is too big, you're going to break it, but this noise was quite large already, and we get a very beautiful signal coming out. And there's no magic, there's no rounding off, there's no nothing. It's just that inverters have very high gain, and so you get a very flat response, very sharp response, very flat response. Any questions there? So this emphasises to you that digital systems are robust to noise. Okay. Now, give me a moment to get back to where we were. Okay, now it's time for a little bit of extra theory. Don't panic, it's nothing too difficult. Like everything, we want to have abstractions. I showed you just before the true signal, it's got these spikes and wiggles and RC timing constants and whatever, and we don't really care about that most of the time. So therefore we replace all of that by just this new concept. And although there are 4 things here, they're all essentially very similar. So there are 4 numbers that we define for a logic gate. If I make a logic gate, I need to tell you these 4 numbers. So I also tell you the contamination delay and the propagation delay, but I need to tell you these 4 numbers. I don't have to describe exactly the input-output relationship and do these simulations and whatever. So what are these magic 4 numbers? V input low. This value, so it might be 1 volt for example, this says that if the input voltage is lower than V input low, then the logic gate will treat it as a logic 0. Maybe I should do this the other way round. I have a logic gate here. Of course, if I put 0 volts in, the logic gate will think it's 0. But what if I put in 1 volt? What if I put in 2 volts? What if I put in 10 volts? At some point in time, this logic gate will stop treating the input as a logic 0. And this number tells us when that is. So, if you have a real-life logic gate, and you guys don't because you use an FPGA, so you're all cheating, but if you did have a real-life logic gate, they do exist, and if you want to make sure that this logic gate works properly, then you have to make sure that your input is lower than V input low if you want that logic gate to think the input's a 0. Now you might think this is a bit silly, you'll just put 0 volts in there. But let me just remind you quickly, you're building this on a printed circuit board and you've got lots of traces operating at high speed. And one trace goes into the input of this chip and you think you're putting 0 volts into here, but you've got noise on your supply rails, you've got crosstalk coming over here, so you're not actually putting 0 into that chip, you're putting in a noisy signal into that chip. And you need to make sure in your design that that noise is lower than this magic number here, this threshold. That's why it's important. Any questions there? And so V input high is just for the other side, that makes sense. above what voltage will this chip treat its input as being a logic 1? Well, that's V input high. It's the same concept, just for a 1 rather than a 0. Now we have a similar concept, but on the output. So the V input low and high, that says if you want this chip to work, you have to put in signals that are either below or above these values. If you do that, if you keep your promise, then the chip promises that its output will be between these two values. Well, not between. It will be either lower than V output low if it's supposed to be a 0, and it will be above V output high if it's supposed to be a 1. The chip, although I showed you beautiful SPICE simulations there with a very clean output, a chip can't guarantee to be that clean. The input might have been noisier, there might have been noise on the supply rails, etc. But the chip does promise that if the input is valid, meaning it's either lower than the low or higher than the high, then the output will be valid, meaning it will either be lower than the low or higher than the high here. And that's it. So once again, we don't worry about what happens in the middle. If the input is not valid, who knows what happens on the output? But once the input is valid, then we have our propagation delay. And then after the propagation delay, the output is guaranteed to be valid, meaning it lies either lower than the low or higher than the high. Is that concept okay? I'll probably have a bit more to say on the next slide, but any questions there? So this is how a chip manufacturer does not have to give you SPICE simulations, does not have to draw complicated waveforms. They just tell you these 4 numbers. And that's enough for you to use their device without knowing, without caring what the actual analog waveforms are doing. That's the key point here. One of the key points here. Okay, so if you've understood that concept, you should be able to answer these questions. Question number 1. For 2 logic gates of the same family, so let's just take 2 inverters. And I'm going to do this with my inverters. And I'm going to apply a waveform here that's down here. It will be lower than V input low, so I guarantee that that's a valid signal here. Or I might apply a waveform and it will be higher than V input high, and that will also be a valid signal. If I do that, then what do I know about the output of this inverter? I don't know its exact value or its waveform, but I do know it will either lie in one of 2 regions, depending on whether my input was a 0 or a 1. If I apply a valid input, I know that the output of this first guy here is either going to be higher than V output high or lower than V output low. So it would be pretty annoying if this chip required an input higher than V output high or lower than V output low. Because if it did, then this design's not guaranteed to work. Because I've done my job, I've applied a valid signal here, and this chip will therefore give me a valid signal on the output, meaning it's either higher than V output high or lower than V output low. I can give you exact numbers if you like. Let's assume that V input low is 1 volt and V output low is, I'll do a silly example, if it's 2 volts. So I apply a 1 at the input. The output here is going to be some number between 0 and 2 volts. It'll be somewhere in here, because that's the guarantee that this logic family gives me that if the output's supposed to be a 0, then the true output voltage will be less than 2 volts. If this logic gate requires that a 0 is less than 1 volt though, then this design is not going to work. Because the chip here only promises me an output of between 0 and 2, and this one requires an output less than 1. So therefore the V output low must always be lower than V input low if you are to be able to connect logic gates together. It shouldn't even just be equal, because remember, I'm going to have noise coming in, crosstalk, thermal noise, etc. So in fact, you want V output low to be much lower than V input low. And the similar thing for the high ones. The greater the difference, the greater the robustness to noise. The more noise you can add between these two gates, and the design will still work. This is a very important concept. I don't think it's difficult once you've caught on. Are there any questions about this concept? Okay, and so in fact we give them names because it's a simple concept but an important concept, so we give them names. We call the difference between the two the noise margin, and so we've got a noise margin low and a noise margin high. And the larger the noise margin, that means the more noise the system can tolerate and it will still function correctly. Any questions? So if you are confused and you are too shy to ask, then just look this up somewhere in the textbook, online or whatever. It's not a difficult thing once you see what's happening. Okay. Okay, so now let me emphasize, as I've been saying before. So early on when I taught you about propagation delay, etc., I used words like when the propagation delay is the time it takes from when the input is valid to when the output becomes valid. Now I can make the word valid precise. The input is valid when it is either above V input high or when it's below V input low. That's when it becomes valid. The output is valid once it's above V output high for logic 1 or below V output low for logic 0. And then with respect to this, we can define precisely what we mean about our contamination and propagation delays. You can also read chapter 1. So, to remind you, but now being extra precise because we can be, the contamination delay of an actual real-world gate that deals in more than just zeros and ones but has to contend with actual waveforms coming in that can take on any voltage level. The contamination delay is a lower bound on the time from when the input first becomes invalid. Now this is important because I might have a waveform that does something silly like this. So this is a silly waveform. It starts off at a logic 0, it transitions to what looks like a logic 1, goes back down to a logic 0, but eventually becomes a 1. And so if you have a silly waveform like this, and often silly waveforms end up on your exam, but if you have a silly waveform like this, then the time you count the contamination delay from and the time you count the propagation delay from are two different times. The contamination delay is when the input first becomes invalid. So here, if this line represents when the input is valid, the input first became invalid right here, the first time it crossed that line. Just because it falls back down again several times, contamination delay is counted from when the input first becomes invalid. And it goes up until when the output first becomes invalid. Because remember, contamination delay is a promise that the output is not going to change. Now, of course, the output will change. As soon as I change the input, the output's probably going to go up a bit. But anything lower than V output low, or anything above V output high, is valid. So the signal at the output can change in the analog world without changing in the digital world. It only changes once it goes from valid to invalid. And that is the precise time you use to measure these delays. The propagation delay is very similar. It's time from when the input first becomes valid. So just because over here it might have become valid, it becomes invalid again, so we don't actually count that. We wait until when the input I should actually rephrase this here. That's a bit confusing. So you have to wait until the input is valid and stays valid. So in fact, that give me time to think about it. That either needs to be rephrased or is just wrong. You wait until the input is valid and stays valid, and from then, from that point in time, you start your stopwatch. When the stopwatch reaches the propagation delay, that's when you know that the output is guaranteed to be correct. So contamination and propagation have the same meaning as before, but we can define them precisely in terms of the V input low, V input high, V output low, V output high. That's all I'm saying. Any questions there? It should hopefully make common sense. You need to define delays from a certain point, so it should all fit in and just be one simple concept. Any questions? Okay. Now I get to correct a small lie. So teaching is often a case of teaching smaller and smaller lies. Like in physics, you first learn that electrons circle the atom, then you find out that's complete nonsense. So I told you that we can model propagation delay by using a transport delay. But then I did warn you that wasn't our final model. Today we'll learn that a better model is using what's known as an inertial delay. And an inertial delay swallows short pulses. And I'll show you that using LT spice so it becomes believable. The problem with a transport delay is that even if I put in a very short pulse to my logic gate, so if I put in a very short pulse to a transport delay, I will still get out a very short pulse at the other end. It's just been delayed. But if you put in a very short pulse to a logic gate, you get nothing coming out the other end because it can't react fast enough, to cut a long story short. And I'll show you that using LT spice right now, I guess. So my claim is, so is it still here? So I've got my design here. If I know what I can do. I am going to set rather than delete it, I'll just set its amplitude to 0. So I get rid of that guy. And this guy, so at the moment, it's got a period of 1 nanosecond and it's on for half a nanosecond. That's why I got a square wave, because it's on for half a nanosecond and the whole period is 1 nanosecond, so it's off for half a nanosecond. If I have it on for just 0.1 nanosecond, and now I run my simulation again. So here you see the green is the input, and the output, well, it hasn't swallowed that. I put a short pulse on the input, and a short pulse comes in at the output. So you might think I'm telling porkies, but bear with me. I make it even shorter. I make it 0.05 nanoseconds. Run the simulation again, and we're getting there. Something interesting is happening. It still shows up at the output, but only just. So now if I make it 0.01 nanosecond and run it, here we go. So I've put a pulse into my inverter, but I get nothing coming out because the output stays below V output low. So logic gate, so this is an inverter, it's a logic gate, an actual one. Logic gates swallow short pulses. If I were to model this using a transport delay, that short pulse would appear at the output. But it doesn't. We get nothing at the output. So if it's a longer pulse, if I have a longer pulse, like 0.1 nanosecond, then we see that the output is essentially a delayed version of the input. The input starts here and stops here. The output starts here and stops there. The output's just a delayed version of the input. But if that pulse was very short, the output is nothing, as in it hasn't changed. So therefore, we refine our model and we model logic gates as having, that's intelligent, we model logic gates as having inertial delays rather than transport delays. Now, of course, even this is an approximation, and if you're enthusiastic, you can look through Verilog and see that you can actually model delays in a more sophisticated way than this, but this is good enough for this course. We just assume that real logic gates have an inertial delay. That's good enough for this course. So a real logic gate is an ideal logic gate followed by an inertial delay. And the effect of an inertial delay is that short pulses get eaten. The only thing to remember, because it took me about 5 years to remember it, is that if I tell you that I have an inertial delay of 2 nanoseconds, what happens if the input is precisely 2 nanoseconds in duration? And so the pulses that get eaten are the pulses that are strictly less than the delay. So a 2 nanosecond pulse will go through, but a 1.999 nanosecond pulse will get eaten. That's just by convention. So for this course, it suffices for us to model propagation delay, not by a transport delay, which we did early on for simplicity, but by an inertial delay. That's a better model. This is how you do a transport delay in Verilog. I showed you that before. This was snuck into the labs and is actually an inertial delay. It behaves differently. Inertial delay is the same as transport delay provided the pulse width is equal to or greater than the delay period. But an inertial delay will swallow any pulse whose duration is less than the delay period, and so therefore this will behave differently from that. For those that are interested, I highly encourage you to read this article in the online repository because I find it quite eye-opening. So at universities we have exams and believe in rigour and precision and everything. But out in the real world, you've got people doing this stuff for a living, and this article basically says most of them are doing things that are wrong. That's not atypical, actually. So it's actually very hard to, Verilog gives you so many ways of introducing what look like delays. It's very hard to know that you're doing it the right way without lots of experience. And so I'm basically telling you either do it this way or this way and no other way. Because this article shows you that in essence almost any other way you find is not going to work properly in all situations. If you don't care, then just memorise this for transport and that for inertial. If you do care, read this article and you should find it quite fascinating. And the best way of understanding something is by implementing it yourself, so that it should be no surprise that this is your homework. And you will send through pulses of different lengths through an inertial delay, and you'll be able to see with your own eyes what happens. For the exam, you will need to be able to do this yourself. If I give you a waveform and say, what's the output if you put this waveform through an inertial delay of 5 nanoseconds, you need to be able to draw it yourself. But first, get ModelSim to draw it for you, or an online Verilog simulator. Get it to do it for you first, and then you can learn the trick yourself. Now, I'm expecting that to be the last slide. And since that does nothing, it really is. Okay, thank you.